Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have just seen how to calculate or how to compute the expression of probability of error, first for BPSK or binary pulse amplitude modulation, and then we have extended the method to Emery pulse amplitude modulation. So, what we will be interested to see now is the graphical representation of the results, because typically the results are in terms of Q function or in terms approximated as exponentials, which are not very easy to visualize. So, we would like to see the graphical results, which will give us some intuitive feeling of what happens to the probability of error as you change EB by N naught or as you change the parameter M. So, as we see this particular expression here that we discussed in the previous lecture, what we find that probability of error for the symbol error, this is the probability of symbol error for Emery PAM is given by 2 m minus 1 upon m, and we have seen the reasons for this, 2 being we are taking both sides of the tail, and m minus 1 upon m because we have m minus 1 complete PDFs. So, inside the Q function you have EB by N naught, because in digital communications we are interested in EB by N naught, that is average SNR per bit or average energy per bit, because the basic unit of communication is bit. So, we want to compute how much of energy or SNR per bit is used in order to actually communicate. And there again you have some further multiplicative factor where there is k log m base 2, and in the denominator there is some more factor. So, now moving down further with this, we have defined what is of course EB by EB AV, that means the average bit energy in this part which we discussed earlier. So, and we have already said that the probability of error expression is rather expressed in terms of average SNR per bit rather than SNR, and this usually is denoted by gamma b, and gamma s is usually used to denote the signal to noise ratio of the symbol. So, this you could write it as k EB by N naught, which is k times gamma b. This is what you can consider. So, what we see over here is this axis that we have drawn is the probability of symbol error Pm, which you have just derived, and this axis is the SNR per bit, which is gamma b dB in decibels. So, we are looking at in decibels form, because generally the SNR is represented in decibels. The first curve that we have over here is the result for m equals to 2 binary PAM, which we have discussed before, and it can also be obtained from the Emery PAM result. So, then we look at the result when m is equal to 4, that means 4 point constellations minus 3D, minus D, D and 3D. So, in that case the probability of error results looks like this, and as we increase m, that means as we increase the constellation size, the probability of error curve shifts on the right. So, it can be read in 2 or 3 different ways. So, one of the ways to look at it is, as I increase the size m, right, the SNR per bit required to maintain the same probability of error increases. You can clearly see that this increases, right. The other notion that you can also see is, given a SNR per bit, there is a certain probability of error required for m equals to 2, which is approximately 10 to the power minus 7 over here for the particular case that I am considering. As I keep my SNR per bit constant and I move to a higher order constellation, the probability of error increases. The probability of error simply increases. So, if I would draw a line along this direction, I can only find that if my SNR per bit is maintained constant, the error probability increases. So, what it means, the message that it conveys is that if we are increasing the constellation size, that is m, the energy per bit that is required to maintain the same probability of error is going to increase. Or if I am going to maintain the same energy per bit, but I increase the constellation order, I will be getting into more and more errors, right. So, why does it happen? So, one can intuitively analyze this, and then one can see exactly how does it happen. So, if this is my signal space x axis, there is a 0, and you have the first situation where it is d and minus d, there is a certain probability of error. So, now if I have to maintain the same probability of error, that means I have to maintain the same minimum distance, I have to increase the signal energy. So, when I am going from m equals to 2 to m equals to 4, by keeping the same minimum distance without changing the minimum distance, because we said error probability is dominated by the minimum distance. If I have to keep the same minimum distance, I have to increase the size of the constellation. That means I have to increase the energy of the constellation, the average energy goes up. So, that means if I have to maintain the same error probability, that means keeping the same minimum distance, average as energy required simply increases, right. So, this is the first part. The other view is, if I want to keep the same average energy. So, let us take m equals to 4, I want to keep the same average energy m equals to 4. However, I want to use m equals to 8. So, if you want to use m equals to 8, in that case we have to accommodate more constellation So, it is not to scale, right. So, that means I have to pack more symbols within that same average energy. So, that means the PDF now n naught is unchanged. So, the variance of noise is unchanged. So, that means if I maintain the same signal power, the variance of noise as experienced would be the same, which is the spread of the signal, right. So, if the variance of noise has remained the same, the way you could keep the error probability the same is by maintaining the same minimum distance, because you are interested in calculating the area under the tail probability, right. So, which will be remain the same if this distance is kept constant, that means this area is remaining constant. Here what is happening is the constellation points are coming closer, right, compared to the previous case. So, you have one constellation point, you have another constellation point, you have another constellation point, you have another constellation point. So, that means you are now integrating this area. Previously you were integrating area which is much smaller, that means you had 3D over here. So, your area under the curve was here. So, that means we could see a clearer picture. In one case your area under the curve was here, but now if you pack more signals, PDF is not changing, but the area under the curve is changing. Right? That means you cover more area under the curve, because the PDF is unchanged, the signal power has remained the same, the noise power has remained the same, the variance has remained the same, only thing is our thresholds have come closer, right. Here wherever was one threshold, here the threshold is much closer. So, if the threshold is much closer, area under the curve is much more. So, that means the error probability increases, and that is what we exactly have here. If I keep my same energy, in that case if I increase m, my probability of error increases. So, these are the two views that you can get from this particular figure. So, now if we go ahead and try to understand that what could possibly making this happen, that is intuitively what we have explained till now. So, instead of explaining intuitively, if we look at the expressions, things will be a bit more clear. So, what we do is, let us take the PAM, whichever we are doing right now. The d minimum Euclidean distance is given by this, which we know, and d mean squared is of course this expression. So, if we keep d mean squared constant, we are going to get this nearly the same Pm, that is what we explained. So, as k increases, by this arrow I mean k increases in the upward direction, it means it increases, m increases exponentially 2 to the power of k, right, it increases several times faster. E average increases to maintain the same probability of error, that is what we have already explained, because if you would keep the same minimum distance, you would go from 2 to 4, your error probability is going to remain the same, right. Or if you want to keep the same E average, in that case your probability of error increases, that is what we have seen as m increases. This is because symbols are more closely packed, and if symbols are more closely packed, the minimum distance decreases. If minimum distance decreases, probability of error increases. This is what we have seen qualitatively. Further, you can also note that the probability of error is proportional to e to the power of minus EAV upon 2 to the power of k squared. We have the term, because we have to look at the expression of error probability, which is here. So, from this you can say that Pm is less than or equal to 2 m minus 1 upon m e to the power of square of this, that is minus 6. I am going to use k, because log base m2, I am going to use gamma b, which is equal to gamma, and this is equal to gamma b. So, this is gamma b divided by 2 to the power of k squared minus 1, right. So, that is what we have. So, that is what we said in this particular expression as well. So, when we use this particular expression, we have not considered this part, because as m grows, this number almost becomes close to 1. So, as m becomes larger and larger, this is close to 1, this is a constant, there is not much effect, not much variation with m over here compared to what we see over here. So, m is log m is 2 to the power of k. So, there is not much variation with k. So, now if this is fine, we move ahead. If you are okay with this expression without the constant term in front of it, so we use the proportionality. So, what we have is this expression. So, for constant E b by n naught, as k increases, so we are maintaining this ratio as constant, because this is constant. So, average bit is constant, the exponent of E decreases very fast. So, let us see. So, you could write this as minus alpha, right, which you could write e to the power of minus k upon 2 to the power of k squared minus 1 multiplied by gamma b, that is what we have. So, the exponent is k E b a v upon 2 to the power of k squared minus 1 upon n naught. Now, clearly you can see that if k increases, E average increases, of course, the numerator increases, but the denominator increases at a much faster rate, because it is 2 to the power of k squared, right, or 2 to the power of 2 k. So, going by this, for k increasing, the alpha decreases at a very fast rate, and therefore, e to the power of minus alpha increases. E to the power of minus alpha increases means probability of error increases. So, clearly from the expression also you can get a view of what happens as you increase k. So, in summary, what we can say is that in these kind of constellations where we are having more bits to be sent, that means we would have to recall a previous discussion, or we will use this particular one. For this, k equals to 1, for this k equals to 2, and for this k equals to 3, that means 3 bits, right. So, what is happening on the other side? On the other side, if your bit duration t is constant, right. So, then your bits per second is k upon t bits by second, bits per second. So, as k increases, if this is your bit rate, let us say b increases, bits per second increases. However, what we see, Pm also increases, that means probability of error increases. So, on one hand you have an improved throughput, but you have a poor error probability, right. So, if you decrease bit rate, you will decrease your bit rate, that means you are decreasing number of bits per symbol. So, as I increase m, we are sending more bits per symbol. So, if I am using binary PAM, I am going to use only 2 levels. If I am using quaternary PAM, I am going to use 4 levels, 1, 2, 3 and 4. So, in this case I am sending 2 bits per symbol, in this case I am sending 1 bits per symbol. So, in the 1 bit per symbol case, my bit rate is low, but my probability of error is good, is also low. When I send more bits per symbol, I pack more bits per symbol without changing the total transmitted power. In that case, my bit rate has of course increased, but my error probability has also increased, right. So, in order to maintain the same error probability, I must use much more energy, right. We will see an exact comparison later on. So, at least it tells you that by going from one constellation order to other, that is going from binary PAM to emery PAM, m equals to 4, 8, 16, you are definitely increasing your bit rate, but if you are keeping the same transmit power, your error probability increases significantly. So, when you are increasing bit rate, in order to maintain the same error probability, you must increase your transmit power as well, right. If you do not, then your error probability would increase significantly. So, this is something that we should remember. So, with this we can move on to the next very important thing or the related thing that we have studied is quadrature amplitude modulation. And at this point we can remember that when we discussed QAM, we have said that QAM can be composed of 2 PAM signals, one along the I axis, one along the Q axis. So, what we had said is that if there is PAM along this axis and there is PAM along this axis, right. So, then what you have is a QAM. So, any constellation point can be thought of as a PAM here and a PAM here, right. So, if I receive a signal, I am going to project its component on the I channel and I am going to project it on the Q channel, and I can use PAM for decoding. So, whatever we have studied for PAM, we can now extend it to the analysis of QAM when we are doing error probability analysis. So, let us look at the study of probability of error for QAM. So, again to summarize, what we have is the signal in this form, which is not new to you. So, I do not need to spell it out, and the signal vector is in the next line again, since it is known and described thoroughly in all previous lectures. Again I leave it up to you to connect. The probability of error computation that we will do is now going to be shown will depend upon the constellation. So, what we are trying to say is we have qualitatively said that the d mean squared is affecting the probability of error, we are going to slowly get into the impact of such a thing in this particular discussion, right. So, let us consider, and just for the second I would like to remind you that when we studied QAM, we said that the choice of the constellation would depend upon several factors. So here we see one of the factors, at least one of the factors which should influence the choice of the constellation or the design of the constellation. So when we compute the probability of error, let us take one situation where we have two possible constellation. So in these two constellations, these are the symbol locations. So in both the case, m is equal to 4. So there is no problem on n. We have 4 constellation points. That means k, that is number of bits, is equal to 2. And we have maintained that the minimum distance between two constellations is 2a. So now we are saying that both the constellations have the same minimum distance. So minimum distance is 2a, you can be rest assured that there is not much impact on the probability of error, right, it will remain the same. And if you would calculate the average power, that means here it is 2a squared and you have 4 2a squared and divide by 4, because of course we are taking equiprobable, you are going to left with 2a squared as the average power, because this is 2 root 2a. If you look at this constellation, there is a particular description that is given. Again, the average power would turn out to be 2a squared. Now, since the minimum distance is same and average power is the same, there should be no difference in terms of error performance. So, if you plot the probability of error versus signal to noise ratio for these two, they will turn out to be the same, right. So, as you increase the SNR, the error probability will decrease in the same fashion. However, you may observe in this case that all have the same energy, which is not true in this case, right. The energy of this is less than the energy of this. However, we have maintained same minimum distance and the same average power, right. So, this has lower power and this has higher power than the average, and average would be same as this, right. So, these are constellations which are closer, these are farther away. So, overall it has been maintained. So, that clearly means that peak power to average power for this is much smaller compared to peak power to average power. So, the peak power in this case will be higher, the peak power than the peak power in this case. So, now if you have a requirement where the peak to average power ratio, which is an important parameter for signals passing through nonlinear power amplifiers, and you have a certain ratio which constrains your requirement, then you are going to definitely go for this particular constellation, which has much lower peak to average power ratio compared to this. So, although these have the same error probabilities, these have lower PAPR, peak to average power ratio, and hence I would prefer to go with this particular constellation. Moving ahead, let us take the situation for m equals to 8. So, in case of m equals to 8, we have example where this particular one is one constellation configuration, right. Another constellation configuration is the one, and I am marking with red as the constellation points, right, and they have been labeled. So, you can look at the exact labels and do the calculations yourself. I am not spending time in doing the calculations here, because that is not a very complicated job, you should be able to manage that. So, we are mainly focusing on the message that is being conveyed. So, we have the fourth constellation which I am filling up here, the fourth constellation is here. So, if you look at all of these constellations, they all have m equals to 8, and the average power calculation is simply represented here 1 upon m, m is 8, sum over m equals to 1 to 8, that means I will take the power of this is AMC squared plus AMS squared, which is written over here. Then I will go to m equals to 2, I will calculate the power, which is the norm squared of this vector, then I will calculate the norm squared of this vector, and so on and so forth. So, I will be able to calculate the sum of the power of all divided by the total number is going to give me the average power, right. So, that way I can calculate the average power of all these, and what we have noted down here, the average power of these two constellations is 6a squared. We have also maintained the d mean as 2a, just like the previous constellation for m equals to 4, so that all the constellations have the same probability of error, right. So, these constellations have a certain average power. These constellations you can see has an average power requirement as given by this, and this constellation has an average power requirement which is given by this expression. So, what we find is that although all of them will enjoy the same probability of error, but that is arrived at by spending different amount of power. And clearly what you can see is this particular configuration here requires the least amount of power, and hence this constellation is possibly one of the choices which can be used, because by spending less power it achieves almost the same error probability as any other constellation. So, through this at least we can explain that when we go into QAM, the choice of constellation is not a very straightforward solution. So, we need to look at least one step deeper in order to select the constellation for QAM. If we are taking m greater than or equal to 16, then rectangular QAM requires only slightly higher power than circular QAM or any other thing. So, what we mean is that if you choose another constellation, you could make many possible constellations. So, all we are trying to say is that if you are using a rectangular QAM, the extra amount of power compared to the best constellation in terms of minimum power would be only slightly more, and we are willing to pay this extra price, that means slightly more increase in power, because we have a huge advantage in terms of ease of demodulation, because if demodulation would also require some power, right, some processing power. So, we would like to reduce on that front and make algorithms much simpler. So, for rectangular QAM, you have m equals to 2 to the power of k, where k is even. You have rectangular QAM, because even means you have I axis, you have k axis. So, you have on 2 axis you would like to choose k even, so that you would be able to divide the bits evenly amongst both of them. So, QAM is basically 2 PAM on 2 quadratures, with PAM each having root m signal constellation. This is clear, and we have always drawn that several times. So, this I do not need to explain. If I have 1, 2, 3, 4 and I have 1, 2, 3, 4. So, 4 PAM and 4 PAM would make 16 QAM. Well, this is well known, right, we do not need to describe this much. So, in order to calculate the probability of error, we look at the probability of symbol error for root Emery PAM, where E average is the average SNR per symbol for QAM. So, there we had a 6, but here we have a 3 because of translation of variables. So, the average probability of error for root M PAM looks like this. So, for calculating the probability of error for QAM, we would have to calculate the probability of the symbols being correct on both the directions. So, if root PM is the probability of error, 1 minus P root M is the probability of it being correct. So, both the symbols have to be correct. So, you have these dimensions. So, it has to be correct here, it has to be correct here. So, when both are correct, so probability of correct in one direction multiplied by probability of correct being the other direction, because these are orthogonal dimensions and we have Gaussian noise, we consider these to be uncorrelated, which leads to independent. So, based on which we have this 2 PDFs getting multiplied, probabilities getting multiplied, we have the square term. Now, 1 minus probability of being correct is the probability of error. So, you can substitute this expression inside this and you are going to get the probability of symbol error for QAM. And then once you do that, your probability of error expression, you can fill all these expressions over here, and then you can make the approximation that as m increases, instead of having this one, since 1 over root m decreases, you can simply say that p root m is p m has, which is less than or equal to this expression here, and it can further be stated that it is less than 4 q. You have to square this, 1 cancels out, you are going to have 4 q squared and you are going to have 4 q. So, q squared is much less. So, you can make an approximation again less than 4 q, and for non rectangular q a m you are going to get an expression which is represented over here. So, up to this step one should be able to easily arrive at by using the expression for p I m. And we would also like to remind you at this point about the possible expression for Emery PSK, which we are not deriving here because we have many more things to do. So, that can be derived using the procedure which we have followed. So, you can break it into components and you can still derive. And we will look at briefly the error probability curves, and we will continue to see it in the next lecture. But very briefly, what we find is I have marked in red the probability of error of Emery QM, and in black is the error probability for Emery PAM, and these lines basically almost merge with the black line. So, just to make it separate, we have made another line. So, as probability of error increases, decreases, these lines match with that of the PAM. So, what we see is that as m increases, so this is m equals to 4, this is m equals to 16 and this is m equals to 64, the error probability behaves exactly same as that of PAM. As m increases, your SNR required to maintain the same error probability increases, and for a constant SNR, as m increases, your error probability increases. And the reason need not be explained any further, because we have already explained the reason why it happens for Emery PAM, and QAM is constituted of two such Emery PAMs, one along the I channel, one along the Q channel. So, all the descriptions and explanations that we have given for such kind of behavior for Emery PAM would apply in exactly the same way for Emery QAM. So, we stop this particular lecture here and we continue with these discussions further in the next lecture. Thank you.